Meet the Adidas Trionda, the official match ball of the 2026 World Cup. Built from just 4 panels, it features a side-mounted 500 Hz tracking sensor, delivering real-time referee data and unmatched aerodynamic stability for the beautiful game.
The 2026 official match ball functions as an active, high-frequency sensor platform, broadcasting its physical state 500 times per second while moving through a stadium. This is the Adidas Trionda, the official match ball of the 2026 World Cup, hosted by the United States, Mexico, and Canada. Functioning as a data instrument on a soccer pitch requires surviving a remarkably hostile mechanical environment. Professional athletes strike the ball with massive kinetic energy, repeatedly compressing its structure against turf, boots, and goalposts over 90 minutes of continuous use. Placing fragile silicon microchips inside a high-velocity impact projectile creates a massive engineering contradiction. You have to protect the electronics without altering the physical behavior of the ball. To solve this, engineers faced a compounding series of design challenges. First, they had to manipulate the fluid dynamics of the exterior shell using erratically reduced panel count. Second, they had to preserve the ball's perfect center of mass despite inserting asymmetrical hardware. Finally, the internal hardware had to transmit data fast enough to overcome the inherent latency of optical tracking cameras in the stadium. The Trionda succeeds through rigorous systems engineering. Material science, mechanical balancing, and data fusion are entirely codependent. If one system fails, the entire ball ceases to function accurately. The exterior of the Trionda is constructed from exactly 4 thermally bonded polyurethane panels. This is the lowest panel count in World Cup history. A low panel count presents a specific fluid dynamics problem. Fewer panels require fewer seams, resulting in a much smoother surface. At high speeds, completely smooth spheres suffer from highly unpredictable boundary layer separation. The historical precedent for this issue is the 2010 Jabulani ball, an 8-panel design whose relative aerodynamic smoothness led to infamous erratic flight trajectories. This graph plots drag coefficient against Reynolds number, representing speed. Notice this steep drop-off, the drag crisis. Here, air resistance sharply drops, causing chaotic flight. Over a completely smooth sphere, the air's boundary layer separates early, generating a large, unstable wake that dictates erratic movement. To counter this on the 4-panel Trionda, engineers introduced deep macroscopic grooves across the exterior shell. They paired those deep seams with a secondary countermeasure, heavily embossed microtexturing stamped directly into the polyurethane panels. This 2D cross-section illustrates how that texture affects airflow. By artificially increasing the surface roughness, engineers force the boundary layer to transition into a turbulent state earlier. This turbulent air actually hugs the curved surface tightly, exiting with a narrow, stable wake. This stabilized boundary layer effectively locks in a predictable drag coefficient, ensuring the ball reacts consistently to high-speed actions, like a high-spin power tribella. Paradoxically, to guarantee smooth, predictable flight dynamics, aerodynamicists had to make the surface significantly rougher. Engineering a stable aerodynamic shell solves the flight dynamics, but that stability is useless if the internal mass of the ball is unbalanced. In previous generation match balls, like the 2022 Al Rihla, the digital tracking sensor was suspended in the exact center of the internal bladder. That design relied on high-tension cords, vulnerable to extreme compression forces from heavy strikes, complicating the manufacturing process. For the Trionda, designers shifted the architecture. They removed internal cables, moving the tracking module to a side-mounted pocket embedded directly into an outer panel. The Connexin tracking sensor housed inside that pocket weighs exactly 14 grams. Placing a 14-gram mass asymmetrically shifts the center of gravity. Kicking a spinning projectile with an offset center of mass causes it to wobble violently. The engineering solution to this asymmetry is dynamic counterbalancing. Precise counterweights are embedded into the opposing 3 panels. These inert weights perfectly offset the sensor's mass, correcting the physical center of gravity. By introducing precise physical asymmetry into the outer shell, engineers successfully isolated the hardware from internal impact forces while maintaining a perfectly isotropic mass distribution. The connection chip embedded inside the panel relies on two primary components, an inertial measurement unit, or IMU, and an ultra-wideband radio transmitter. The IMU is responsible for tracking the physics of the ball, specifically measuring linear acceleration in 3 dimensions, gyroscopic spin rate, and magnetometer orientation. Capturing and transmitting this telemetry continuously creates a strict power constraint. The ball must power an active radio transmitter for a full 90-minute match, plus extra time, without adding heavy, destabilizing batteries to the payload. The solution relies on low-power wireless induction charging. The ball simply sits on a charging pad in the tunnel for 90 minutes prior to kickoff. To conserve that charge, the chip runs an automated power management algorithm. It remains in deep hibernation until it detects a specific acceleration threshold, at which point it wakes up instantly to record the impact. This highly efficient power architecture ensures the ball can continuously broadcast its structural and spatial data 500 times per second without dying on the pitch. That high-frequency data broadcast enables the primary operational application of this advanced hardware system, semi-autodative offside technology, or SAOT. The highest friction point in offside officiating is determining the exact millisecond a ball leaves the passing player's foot. Traditional optical tracking systems suffer from inherent latency. Standard stadium cameras operate at just 50 Hz, meaning they only capture one single visual frame every 20 milliseconds. This diagram maps a 20-millisecond timeline. For a sprinting athlete, a 20-millisecond gap creates a massive visual blind spot. A player's relative position to the defensive line can change entirely within that unrecorded window. The Trionda bypasses optical latency by using its internal IMU, which samples data at a much faster 500 Hz. Operating at 500 Hz provides a distinct data point every 2 milliseconds, effectively eliminating the camera's blind spot. This line chart represents the ball's internal telemetry. To find the exact kick frame, the system scans the data for a massive exponential spike in linear acceleration, locking on to the true millisecond of impact. Once that timestamp is secured, the system executes data fusion. It merges the ball's exact timing and spatial ultra-wideband coordinates with the Hawkeye skeletal tracking data gathered by the stadium cameras. Feeding this fused data stream into an AI model generates a sub-millimeter 3-dimensional offside line instantly. Semi-automated offside technology relies on the ball mathematically proving when the kick happened, bypassing the need for optical cameras to see the contact. The internal IMU's 500 Hz sampling rate is highly sensitive enough to detect physical interactions far smaller than a full-force kick. It registers minute micro-vibrations and fractional changes in angular momentum across the polyurethane shell. This sensitivity provides definitive touch detection. When a grazing handball occurs that is visually inconclusive on standard camera replays, the IMU successfully registers a distinct vibration transfer, resolving the dispute instantly. It applies the same logic to mid-air deflections. Identifying an intermediate touch on a pass instantly alters the timeline used for an offside calculation. The system provides empirical mechanical data to verify contact, replacing the subjective interpretation of a human referee attempting to parse blurred, slow-motion video. The Trionda requires successfully manipulating boundary layers across a 4-panel exterior, while precisely balancing asymmetrical tracking hardware on the interior. These specific engineering feats exist solely to support the continuous, high-speed telemetry required for modern officiating. The Trionda represents a convergence of material science and high-speed telemetry. It produces an environment where the football itself provides the empirical evidence required to resolve the game's most contentious moments.